Okay, something going on with my computer. I'm not liking it. Okay, so so we've got basically 1 week left. We've got today's lesson and 3 lessons next week. The idea is in today's lesson, I'm going to go through a couple more trickier expansions, but after I've gone through a bit of board work, you can spend the rest of the time working on the factorization puzzle sheet. And I've got other things that you can focus on as well if you want to practice something in particular. Um, Monday's lesson, we're going to have a look at some application problems, just a lesson on that. Having a look at, here's a word scenario, let's turn it into an algebraic expression, which we can then use to solve for it. And then Tuesday's lesson, we're going to have a bit of a revision lesson, and the revision lesson is going to center around this. I'm going to give you, it's a fairly short assignment. It's just a 2-pager like this, and it's all spaced out. So it's not that much to it, but it's a mixture of expansion and factorization problems. And my thinking is, obviously I'm not going to be, if you hand it in on Tuesday, there's no way I'm going to be able to mark it in time for the test, but we might just spend Tuesday doing a self-mark. So we'll go through stuff. You can, and it's a good thing to do anyway, because it really sharpens your mind on what you know and what you don't know as well in a self-mark. So we'll do that on the Tuesday, and any time left over for revision, then the Thursday will be for the test. So I'll pop these here. If I have a chance, I'll wander around and give them to you personally, but otherwise make sure you don't leave without that particular sheet. Your factorization 1 homework, I just haven't had a chance this week to get through it, and not everyone's handed it up yet. So I know there are a few people that did. Hello, welcome. I know there are a few people who didn't hand it up because they weren't here when they got it, and I've discussed that, so that's all good. But if you were just absent when you're supposed to hand this up and you've still got it in your hot little hand somewhere, can you make sure you give it to me, because I will be prioritizing marking that. And what I think I will do is, if I can get it marked before Monday, I might even try and see if I can scan it and return it to you earlier, just so you've got it back earlier than that. But otherwise, it will be done by Monday, so that at least you've got something to look at in terms of what you're mastering there. The other thing I just wanted to point out is that I've got 10 blank copies of the quiz. I remember that Charlie, and Fergus asked for a copy, and there were 7 others of you that put your hand up. So I've got copies for you. If I run out, I can always print out more. But that's for those. There were a number of people who said, I'd just like a blank copy of the quiz so I can do corrections and stuff. So that's for you guys as well. So I'll come around for that in a second. Just a reminder as well, for the video, I'm just holding up random pieces of paper, that there's the how to factorize a handy flow chart. Everyone received one of these, and it was supposed to be glued into your summary book. And so make sure you're referring to that and having a look at it. If you've lost yours, I do have some spare copies here. So just keep that in mind. And I think that's all the admin I wanted to go through before I do a little bit of board work. Does anyone have any questions or comments about that? No? Okay. I can't remember if I mentioned this or not, but this is the other worksheet that I've got. This is a single sheet, and it's different factorization problems. I was going to hand it out earlier. It's got like identify which one you would use, but you could actually do the problems themselves, I reckon. Okie dokie. So I'll leave it at that, and welcome, Charlie. Oh, thank you very much. I'm happy to be here. So I'm just picking and choosing some of the ones that weren't necessarily done very well. And again, we hadn't really covered it in class, so it was a bit of a check on that kind of stuff as well. So this expansion here is p+1 all cubed. So what do you reckon, what can we do? I guess, is there a highest common factor? No, there's nothing there. Does it fit a pattern? Yes and no. The yes is yes, but. The answer is yes, but you guys don't know it unless you know it off your own back. It's called a Pascal's triangle expansion. But we have not looked at a cube. We've looked at a square, that's a squared plus 2ab plus b squared, or a squared minus 2ab plus b squared. So we know a square, but we don't know a cube. And what I see people do often is say, well, it kind of looks like it should be a pattern, so I am going to just try and force it to the pattern that I already know, the square pattern. You can't do that. It's kind of like saying, I've got a foot and I've got a size 2 shoe. Well, I reckon I can squeeze my foot into it. But it's not the right, it's too big, right? It's not the right shape. So you can't just, I call that mathemagic, when you, for no real good reason other than it kind of looks similar, you try to fit the pattern. It doesn't work. But what do we know about cubes? What does a cube mean? Charlie? What does to cube something mean? Yeah, exactly right. Times itself. So if I had a cubed, that'd be a times a times a, right? Well, guess what? We can do the same thing here. We can break down p plus 1 all cubed to p plus 1 times p plus 1 times p plus 1. Okay? Now, people forget you can do basic things like that. And then you go into Mathemagica land and you start doing rando things. Okay? That's because people have this bias against algebra. Algebra, they think, is magic. Algebra is something that belongs in its own la-la land. And all the rules don't apply. Up is down, down is up, left is right. It's opposite day. Thank you, Justine Clark. That's how they treat algebra. But that is not true. Mathematics is intrinsically logical. The rules that apply across the board of mathematics. And usually the reason why they see mathematics or algebra, as something which is magical is because they forget that P, in this instance, is just a number. It's just, how many times have I said this now in this class? Millions of times. Variables are just numbers. P does not stand for penguin. It's not penguin plus 1 cubed. It's not an object. Don't objectify your variables. Those variables stand in for numbers, not objects. And P plus 1 is just an unknown number plus 1 of it. If you can cube 2, you can cube P plus 1 cubed in the same kind of idea way. In this case, by putting it as 3 separate factors. Now, if you've got 3 factors like I've got here, there's a couple of things you could do. You could multiply these 2 together first, and then multiply the result by the third one. Or you can multiply these 2 first and multiply the result by that one, just like you can in numbers. I can go, let me just choose 3 different numbers just to illustrate what I'm saying. If I have 3 times 4 times 5, I can say, well, that's 12 times 5, which is 60. Or I can go, that's equal to 3 times 20, which is equal to 60. Even if I want to, because they're all multiplications, I can even go 15 times 4, which is equal to 60. Either way, when you've got 3 things multiplied together, you know this, right? This is like not even grade 7. This is primary school. That, I mean, we put fancy words like we say that multiplication is commutative, which means it doesn't matter the order in which you multiply things. So we can put fancy words to it, but you know this from primary school. What makes it hard, of course, is I've just chucked in some letters. Not some lettuce, because I'm not a rabbit, but letters like P and then P plus 1, okay? So we apply the same sort of logic that I can take any pair and I can multiply them together. Now, I'm going to pick these 2. Hang on, let me just erase this first. Blip, 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 blip. I'm going to pick these 2 because I kind of like the idea that I'm going to have a binomial, a two-part expression multiplied by a trinomial in the end. But I'm not going to expand it using my chicken beak method, and I'm not going to expand it using my box method. Why not? Someone raise your hand and tell me. Raf? It is slower, because there's a shortcut. And what's the shortcut, Raf? Not sure? Okay, someone else. What's the shortcut I can apply? What do I have to be really good at recognizing? Stella. It is a perfect square. Well done. When I multiply one thing by itself, we're squaring it. It doesn't matter whether it's A or 7 or P plus 1. It's the same thing multiplied by itself. So I'm not going to do this, but what I'm really saying, that's P plus 1 all squared. Okay? So I haven't touched the first factor yet. I can see some rustling going on. I think it's because people are starting to write stuff down. Good idea. So I'm going to factorize the second part there, the bit in red, and I get P squared plus 2P plus 1. And you know what? If you're asked to show some working out, it wouldn't help to put in square brackets PS off to the side. And that says that's what I just did. So as the reader, if the reader's wondering how you went from the first blue line to the second blue line, I've got a reason over on the side. This is schmicko communication. It's really schmick when you put reasonings off to the side. They are, instead of doing it by hand, are working out by hand. So I strongly recommend it. Now I can use some kind of method in order to expand this. This is now an expansion of a binomial by a trinomial. I could use box method. I could use chicken beak method. I could use inspection, although it's a bit, like I said last lesson, it's a bit tricky. I'm going to use the chicken beak method. So I'm going to go this times this, this times this, this times this. And that gives me P times P squared is P cubed. P times 2P is 2P squared. And P times 1 is P. And then I'm going to go this times this, this times this, and this times this. And remember what I said about how to set it out? Yeah, underneath, good, yeah. So 1 times P squared is P squared, good. 1 times 2P is 2P, and 1 times 1 is 1. Now I can just collect like terms by adding the columns up, which is why I like this sort of method. Done. So it's multiple steps. And again, mathematicians, particularly, actually, you know what? It's the fragile, brighter students. And they say, well, if I can't do it in one step, no, Siri. If I can't do it in one step, I must be doing something wrong. As if that's what makes you a good mathematician, is that you can do it in one step. But I think I've said this a few times now, haven't I? Good mathematician, what? Yep, what else?
Gets the answer.
Eventually. No. Oh, yeah, logical. Raf?
They know how and why to get to the answer.
Yeah, eventually. But importantly, a good mathematician will take a first step. Hopefully an efficient step. With practice, we'll know the right steps to take, but it's not meant. You could give me a very unfamiliar problem and I won't know where to start, but I'll make a start. That's what makes a good mathematician. And as you go through the process, you go, hang on, that doesn't make sense, or hang on, that doesn't work. I'll then track back to the start and try a different approach until I get there. So a good mathematician perseveres as well. Okay? It is not a sign of a good mathematician that you can go P plus 1 all cubed, oh yeah, and then go straight to the answer. With practice, you might get there, but not. Anyone see a pattern there with P cubed plus 3P squared plus 3P plus 1? Couple of threes there in the middle, isn't it? So if you look at the coefficients, remembering that the coefficient of a P cubed is just 1, we've got 1, 3, 3, 1 there. So it's symmetrical. Starts with a 1, ends in a 1, and 2 3s in the middle. And we're going to look at Pascal's triangle a bit later in the year. but I just thought I might just point out, don't worry about the rest of the things. But if I just start a triangle of ones here, you'll sort of get, so like this. Now what I'm going to do is I'm going to put a 1 on either end, and I'm going to add up everything in between. So 1 and 1 is 2. I'm adding up the 2 above. So if I put a 1 here, 1 and 2 is 3, 2 and 1 is 3, and 1 is there. I don't know if you see this or not, but they're the coefficients of a perfect square. 1a squared plus 2ab plus 1b squared. And then this one here is these here, 1, 3, 3, 1. So if you want to know what p plus 1 to the power of 4 is, you've got some coefficients that you can start with. Remember, coefficients are the number part of a term, the big number part of a term. Anyway, that's just Pascal's triangle. You don't need to know that at all yet. Okay, let's have a look at this one. I'll keep it zoomed out in case people are still writing. Number 1. Question, comment? No? Very impressive, the people who feel like they don't need to write down the examples. That shows a level of confidence which is impressive and also scary. Raph?
Is it okay to, like, can you use a different technique apart from type of square code to solve that?
There's only other one I know, and that's chicken baking it or box methoding it. But you still have, the thing is, I'm not too sure if this is what you're asking or not, Raph, but I kind of like, if I gave you 3 times 2 times 5, if you're kind of really good, I suppose, you could look at that and say, oh, those 3 numbers, all right, that's 30. But I don't. I go, oh, well, I can see 2 times 5 is 10, so 10 times 3 is 30. So what I'm trying to say is that multiplication is what's called a binary operation. It has an operation on a number on either side of the time sign. So all multiplication really is a process of taking 2 numbers, multiplying it to get to a new number, and then taking that new number and multiplying it by another number. So in this case, I'd go 2 times 5 is 10, and then 10 times 3 is 30. And it's the same sort of logic with this. It's exactly the same logic with number 1 there, p plus 1 all cubed. I have to break it down into its multiplication parts. I have to then choose a pair of them to multiply together. So to start me off. Now, whether I recognize they're a pattern and apply the rule straight up, or whether I do it by chicken beaking, or whether I do it by box method, you still have to end up with an expression, Raf. Does that kind of make sense? So there's no other way other than eventually, when you know Pascal's triangle, there's a shortcut to go from the top line to the bottom line. Oh, right, this is 2 numbers that are added together and cubed, or to the power of 4, or to the power of 7. I can use Pascal's triangle to work that out. But that's just another trick. In the meantime, there's nothing faster that I can think of that you could do. In a test, will I mark you down if you don't use a perfect square? Probably not. I'd have to consult with the other teachers, but probably not. But what are you losing when you do a long expansion instead of using the rule? Yeah, you lose time. So you might not lose marks, but you will lose time. So if we give you a long test and the only way you can achieve it is by, finish it, is by recognizing patterns, shouldn't you recognize patterns? Yeah, of course you should. Okay, number 2 is different from the things we've done before because they are fractions, but they aren't necessarily harder. You're not going to get any fraction work, but I just thought I'd just apply a bit of simple fraction work now because we've got a whole unit on fractions later. So why can't I just add these 2 fractions together? Yeah, thanks for calling out, you guys, but yeah, there's no common denominator. So how do I work out a common denominator, Fergus? Good. And we do that with equivalent fractions, right? Yep. So the basic banal way of doing it is like multiplying each fraction by the other denominator. So this one gets multiplied by 3 top and bottom. This gets multiplied by 2. But you should always check, because actually the number that you should multiply both by is whatever gets it to a lowest common denominator. Okay, so if this was 6 and this was 3, I don't need to multiply this by 3 and this by 6. I could just multiply this one by 2. Anyway, so in this instance, though, I've deliberately chosen it fairly simply. Excuse me, sorry, I need my water. Times this by 3 and times this by 2, right? Now, the important thing is this next line. I think I'll just write in black because it's easier to see. That's equal to 3 outside of 3x plus 1 plus 2 outside of 2x minus 1 all over 6. Does that make sense? Often with algebraic fractions, again, it's, oh my gosh, there's algebra, so we're in la-la land, and oh my gosh, it's fractions, and I hate fractions, and you put la-la and hatred together, and it really mixes up people's results. But it really is just a simple application of fractions. I would definitely do that line that I've just drawn. Some people are tempted to sort of just go straight to an expansion, but I would certainly write that down because it can get a little bit confusing. Now I'll expand it. Like so. And now I'll collect like terms. So 9x plus 4x is 13x. 3 minus 2 is 1. Done. Is that okay? What happens if the variables are on the bottom? Is it different? Not especially. It's the same logic, right? It's the same logic. What did we do in the first one? We found a common denominator. How did we find a common denominator? Just multiply the other fraction by the other denominator. So what am I going to multiply the left-hand fraction by? Can I pick on someone? What about you, Henry? What will I multiply this fraction by? You're being numberist again. What was the logic in slide 2? What did I multiply each fraction by? The other denominator, the other bottom number. Yeah. So what's the other bottom number in this new one? It's on slide 3. 4x minus 1. 4x minus 1. Yeah. So 4x minus 1 is the entire of the left-hand side of that one. Again, remember, this works because if I multiply top and bottom by the same number, I'm multiplying by 1, so it's all good. And what am I going to multiply the other fraction by? James? No. We're going to multiply, yeah, we got good correction. We're going to multiply by the other denominator. Now, it's interesting that you said 1, and Henry said just a number to start with as well until we processed it. You know, it's 4x plus 1, 4x minus 1 is a number. 2x plus 1 is a number. Yes, it's a number that's not in a very simple form because there's a bit that we don't know, the x in this case, but it's still a number. Okay, don't be biased against algebra. It is still working with numbers. Okay, so what does that give us though? That gives us 2 outside of 4x minus 1 minus, I'll put the 1 there, not that I really need it, 1 outside of 2x plus 1 all over 2x plus 1, 4x minus 1. Okay, good news is almost always there's no point in expanding the denominator. In other words, it's better form to leave it like it is at the moment on the bottom. But on the top, because I've got 2 expressions adding and subtracting, I'll be able to simplify that. So you need to expand the top. So I've got 8x minus 2. Now what's this next one though? Minus 1 times 2x is minus 2x. Minus 1 times positive 1 is minus 1. So be really careful when you're subtracting that you're keeping this subtraction all kept together so that you're distributing the subtract across all the terms. Yeah. All over 2x plus 1, 4x minus 1. And now I'm going to simplify the top. 8x minus 2x is 4x. Excuse me, sorry. Minus 2 minus 1 is minus 3. So sorry. You'll have to zoom out a little bit to do it, though.
Wouldn't it be 6x minus 3?
Yeah, thanks. My bad. Technically, you could then factorize the top again. Might be useful. Sometimes it's useful to do it. It's not always useful. What do you think?
Yeah.
So it's just extra expansion work, really, isn't it? I've got one more. Feel free to have it try it first. Try and get ahead of me. You too, James. Harry, have you got paper and pen? Has anyone got loose leaf paper that they could lend Harry a piece or two? It's James. James has got it. Thank you, guys. Very generous, everyone. This is good video, isn't it? If you're watching this again, 2 minutes of silence. Okay, I'm gonna just race through it because I'm, excuse me, I've taken a bit longer than I meant to. So sorry about clearing my throat. So I'm multiplying this by x plus 1 and this by x plus 1, and I'm multiplying this one by x minus 1 and this one by x minus 1. So that gives me a denominator of x minus 1 times x plus 1. Now, remember I said you don't really need to expand that, but if you did, what would that be? What's the pattern there? It's a dots. Yep. And I don't know if you notice this on top or not, but basically I'm multiplying the same thing twice here and the same thing twice here. So I end up with x plus 1 all squared minus x minus 1 all squared, which is another dot. I didn't expect anyone to do dots here, though. Well done on picking that up. In fact, when I formed the problem myself, I didn't even think of that, and I just expanded them. So that's what I mean, though. I think I'm a good mathematician, but it doesn't mean I'm perfect. And although I've really experienced, sometimes I miss those patterns. It's just, it is an effort to recognize those patterns, but it's worth it. So I will use dots this time just to show off, really. So we've got x plus 1 plus x minus 1, x plus 1. Actually, why do I want to do that? I'll do it anyway. X plus 1 minus x minus 1 all over x minus 1, x plus 1. So that's x plus 1 plus x minus 1. That's going to be 2x because the 1 minus 1 cancels itself out. And because I'm running out of room here, I might just show you what I'm doing here. Minus x, right? So x minus x will cancel out. 1 minus minus 1. 1 minus minus 1 is 1 plus 1, so it's 2. All over x minus 1, x plus 1. And so that equals 4x all over x minus 1, x plus 1. There we go. If you'd expanded x plus 1 all squared and expanded x minus 1 all squared and collected like terms, it would be exactly the same answer. 4x all over x minus 1, x plus 1. It's one of those things where I doubt whether doing dots was actually easier in the end, but anyway. Good mathematician reflects on their practice and they go, was that the best way to do it? I don't know. Maybe next time I'll do it differently. A good mathematician does that. Okay. Last couple of minutes, then you can spend some time doing some practice work. I'm now going to switch on to the next slide. So there's all four examples there. But I just wanted to point out that these notes will be available as well as the video on Google Classroom, so you can always go back and review. And if you didn't quite catch up with the notes, they're there for you to catch up with later. So what I wanted to do is a brief summary of what we've learnt in this unit and what you need to be across. The first thing we need to be across is pattern recognition, both ways, for factorising and expanding. So seeing something and saying, oh yeah, that's a dots problem. If I see 4 minus p, 4 plus p, I need to know that I can expand that to 16 minus p squared because it's dots. Similarly with perfect square, I need to know that if I see x plus 2 all squared, I can go directly to x squared plus 4x plus 4 because it's a perfect square. But I also need to know that if I see something like x squared plus 6x plus 9, that's x plus 3 all squared. That's really important for efficiency. Okay, and remember, efficiency in tests means you've got more time to work on the harder problems. So you want to aim for efficiency. Expansion techniques, box method, you would have done that in core maths. Chicken beak method, you may or may not have done it in core maths, but we've certainly done it in our regular maths here. I mean, our maths extended here. Okay, so that's the two expansion techniques really that we've covered. But what we've done is we've then applied them to more difficult problems. So a binomial times a trinomial, or a binomial times a binomial times a binomial. Remember, binomial means something plus something. We've devoted most of our time to factorising techniques. Some of you have used the reverse box method. I showed you the AC method. I showed you the berry method. And I showed you the diamond method. The diamond method was the last one I showed you. The video is up on Google Classroom if you want to see it. It's my current favorite. Just to reinforce that I more or less don't mind which one you choose as long as you pick one and practice it a lot. I think reverse box method is the least efficient. I think the diamond method, although it's a rather opaque method, i.e. it doesn't necessarily make sense unless you investigate why it works, but it is the most efficient of methods. So if you want my advice, practice the diamond method till you get it right. Practice it till you've got it right. But if you say, nah, I just want to do the reverse box method, go for it. It's no major drama, just that you're sacrificing efficiency, that's all. Remember to hook it first, always. So whenever you get a problem, don't go, oh, I better use the diamond method straight away because it's 6x squared plus 12x plus 18. Instead go, wait a minute, there's a common factor of 6 there, take it out first, then you've got a simple trinomial on the inside. Okay, so always hook it and loop. So keep checking every step. So you might accidentally use the diamond method when there's a highest common factor, but once you've broken it down into the two separate factors, one of them is going to have a high, or one or both are still going to have a highest common factor. You can always take that out. It may be that after you've worked it all out, there's still some dots work to do or something like that. So continue to keep looking until it's fully factorized. Okay, so this is what you more or less need to be across for the test, really. This pattern recognition, be able to expand different kinds of problems, be able to factorize using different methods, either by pattern recognition or by using reverse box method or by using one of these methods instead. Okay, before I let you go, does anyone have any questions about that? Okay, so I'm going to stop the video now. You've all got the factorization puzzle sheet to work on, so you can keep working through that. I've also got other stuff up here that you can come and grab if you want to do something a bit different. I don't mind what you do as long as you're doing factorization work, I think.